this is work joint with Hannah Druckenmiller, who's a graduate student at Berkeley. She'll be on the job market soon. And what we've been trying to do is think about the question of whether or not we can eliminate certain types of unobserved heterogeneity in simple cross-sectional contexts. And so what we've done is tried to develop a new technique, what we would argue is a new identification strategy that has similarities to strategies people are familiar with, but we think is novel and involves, it's actually quite simple to implement. And we think it's quite generalizable for not every context, but a variety of contexts. So, as many of you are familiar with, many fundamental questions in economics have cross-sectional elements to them, whether you work in urban or development or applied micro in any context, many macro questions. I work in environmental economics very heavily. And so we have a lot of questions that we were thinking about, questions of, for example, how soil quality affects agriculture is often a cross-sectional question because it's very hard to randomize soil allocation. The challenge with those types of cross-sectional problems is that we have omitted variable biases. This is sort of econometrics 101. It's been talked about in a variety of contexts, and it led to sort of the identification revolution in which people said we need new designs to, try and identify causal effects. So what we want to do is we want to ask the question, can we simply look at a context in which we have cross-sectional data where we have no instruments, and can we try to get as close as possible to something we might consider a plausibly causal effect? And so the solution we propose is that in certain contexts, when you have a lot of units that are densely packed in physical space, you can use that space to organize your observations and make sure that you compare each observation, instead of to the rest of the sample, you only compare each observation to a neighbor. And importantly, you compare every observation to a neighbor. And in doing this, you end up differencing out a very large number of omitted variables. There's sort of two different categories of the types of omitted variables you eliminate, and I'll show you what that looks like. And because you're essentially taking data and differencing it continuously in space, we call it spatial first differences, basically named after the first differences in time series analysis. It's very analogous to what you would do in time. It's just interchanging the notion of time with the notion of space in the data. So just pictorially, to get a sense of what we're talking about, you can imagine you have a large number of homes going down a street. And in a standard cross-sectional regression model, what you're essentially doing is you're looking at a home and you're comparing it to every other home in your sample. What we propose is, instead of doing that, just compare each home to its immediately adjacent next door neighbor. And in doing so, you eliminate large differences that are observed between homes that are far from one another. And instead, you're much more closely approximating a comparison of like with like. So, the key features that make this approach appealing are that it eliminates a large number of omitted variable biases for variables that we don't actually observe in the data. Another key benefit is it's super easy to implement for a lot of different data classes. And part of the reason is because, as I'll show you, you basically can use standard time series operations on your data. You just trick the software into thinking that space is time. And then you can just do everything as if you would have done it in time series. But in addition, and another benefit is that we are increasingly encountering and having available to us these large gridded data sets of all sorts of different variables. And so in a gridded environment, this is particularly easy to implement. And then the last thing I'll show you is that we've actually devised a variety of we think fairly creative internal robustness checks that let you check your estimates in ways that aren't really comparable to anything in the more traditional approaches. And two things I'll point out is that, in order for this to be a valid approach, you do have certain requirements that are different than other strategies. So the first one is that you need observations that are fairly densely packed in space. Now, I don't have a formal description of what that means, but I'll show you sort of intuitively why that makes sense. And I hope some enterprising graduate students will help us figure out what a formal way to define close enough. Okay, and so let's just jump ahead. So let me set up what the problem looks like. So, you have your standard cross-sectional regression model. I don't know, can you guys see my mouse if I move it? You can, okay. So your standard cross-sectional model that we learn in Econ 101, we want to look at the association between X and Y. Ideally, we would want the causal effect. So here, this is the true DGP that I'm writing down. The challenge is that the variable C is unobserved in the data. So if we were to run the standard cross-sectional approach, we would get an estimate beta hat sub L. So we're going to use the sub L as the levels estimate, which is different than the first difference estimate. And as we all know, that this parameter is going to be biased by an amount that is proportional to the correlation between the X's that you do observe and the C's that you do not observe, with a parameter alpha that describes the overall effect of those C's. And so this is omitted variables bias. We're all quite familiar with it. The challenge is that we have this sort of fundamental, so we're interested in the causal effect, which is essentially the change in X, the treatment between two observations, scaled by the parameter beta. And so in the ideal experiment, what we would want to do is we would take some observation I and give it the treatment of unit I, and we would also give it the treatment of some other unit, unit J, and then we would difference those expected outcomes, and that would be the treatment effect we're interested in. The problem is we never observe this right-hand term. We never see, individual I assigned to J's treatment. And so we assume conditional independence, which is basically saying that we think conditional on everything we observe, those two things ought to be equal. And then under those conditions, the levels estimator returns an unbiased estimate, if that assumption is true. And so in a context I'll explore later, I'll be looking at agricultural output. What that basically means is we're assuming if we had a farm in Iowa, which is in the US, very far from Florida. I guess I shouldn't assume everyone's familiar with US geography. So Iowa and Florida are very, very different places. We might assume that, given the same climate conditions, those two farms would otherwise behave similarly in terms of output. What that assumption is in many contexts not thought to be a valid assumption. And so what we're doing is we say, let's weaken that assumption. I'll show you visually quite dramatically, to something that we call the local conditional independence assumption. And so there, what you're saying is not that any farm it can be compared or assumed to behave the same as any other farm, but one farm that's immediately adjacent to another farm might look similar if they are treated the same. Okay, so in this case, what we're assuming is location I would behave the same as location I-1, where we're taking I to index observations across space if they are given the same treatment. And this is a strictly weaker assumption. What you're saying is basically a farm in Iowa would behave the same as a neighboring farm in Iowa if they were given the exact same climate, okay? So to visualize what this assumption is doing, we sort of designed this diagram, this visualization, where you take all your observations in your sample, and they're all going across the top, and they're all going across the vertical axis on this grid. And so each cell represents some comparison between two different observations in your sample. In the standard design, what we're doing is we're making assumptions about comparability or conditional independence between all pairs of observations that we've colored gray. Okay, so in the standard design, we're essentially saying observation 1 is comparable to observation 2, 3, and so on. In the spatial first differences design, we are only comparing each observation to its immediately adjacent neighbor. And so it's a dramatically smaller set of assumptions you need to make in order for the approach to be valid. Okay, so in the right-hand side, we're basically saying observation 1 is comparable to 2, 2 is comparable to 3, and so on, okay? But we don't need to color this whole large triangle. So because this is an assumption, it's something that we can't test directly. But what we want to point out is that this assumption is mathematically very, like that almost identical to the other identifying assumptions that we use in much more common identification strategies. So for example, if you were to do an event study design or a first differences in time analysis, what you're essentially saying is that sequential observations that are adjacent to one another in time and just very close to one another are comparable, conditional on having gotten the same treatment X. If you're doing something that looks like a regression discontinuity research design, what you're doing is you're going to the observations just above and just below the discontinuity, and you're saying, well, those are basically locally conditionally independent, and you're not making comparisons with the rest of your sample. And so again, to bring back this visualization, now what I've done is you see spatial first differences is still on the right, nothing's changed. The cross-section and levels is here. And if you were to look at first differences in time, what you'd be saying is you're looking at observations sequentially and comparing them to one another. Or if you were in a regression discontinuity context, say that X star here describes the location of the discontinuity, you're essentially saying just below and just above the discontinuity, we're going to make a comparison and we won't compare anyone else. And so one way to think about spatial first differences is it's kind of like a continuous generalization of the regression discontinuity approach, where it's as if you can think it's not quite formally the same, but it's as if you are doing a sequence of RDs between every set of neighbors. Now, in practice, you couldn't actually implement a regression to discontinuity between every set of neighbors because you don't have enough observations to estimate that many parameters. And so in some sense, SFD is like the implementable version where we actually are able to achieve an estimator.
Solomon,
okay. Yeah.
I have a quick question. If you go back to the diagram, so with time, you have one dimension. So there's always before and after, and that's fairly clear. But with space, you have two dimensions. So in the diagram to the right, you're assuming that neighbors are those that, well, you do not have diagonal neighbors, for example. So you have to make some assumptions there, right? And I also wonder, how is it very different from, let's say, all the regression discontinuity designs where you look at two sides of a border, for example?
So excellent question. So if you wait a little bit, I'll show you some two-dimensional examples. But one element of this that is interesting is that once you go to 2 dimensions, there's a lot of choices you can make in terms of how you assign neighbors. And that actually leads to ways in which you can take your data and make multiple estimates with the same sample of data. Because you could say, I'm going to compare east-west neighbors in one sample, and then I'll do it again, but only compare north-south neighbors, for example. That's just one way you could do it. And then you're using totally different types of variation in your data to estimate the same number, and you can ask whether you get a consistent estimate. So it's a great question. And maybe if you just wait a few slides, you'll see what we've chosen to do, but I think there's a variety of creative things people could do. And actually some graduate students have already come up with other algorithms that are sort of quite fun.
All right, thanks.
Maybe it's crystal clear what's going to happen, but I'll go through it formally just in 1 or 2 slides so everyone's on the same page. The way the spatial first difference estimator works is you simply write down your data generating process that you think is true, and then you write it down again for a neighbor. So here I is location and I-1 is a neighbor. You take the difference, and what is nice is that we think that the omitted variables bias of this estimator, it may not vanish, but it should be dramatically smaller, okay? And so essentially what you do is you take your x's, you difference them, you take your y's, you difference them, and then you just do a regression of differenced y on differenced x. This regression can be solved, the regression I've written down here could be solved using a variety of fitting procedures. And so in this particular paper, what we've done is we explore the properties of the OLS estimator, but you could solve this via Ridge or any type of MLE. Like there's no restrictions on how this equation is solved. In the OLS setup, it's actually very easy to write down exactly what the estimator is. And in that context, what you end up with is having a condition here for unbiasedness, which we call a local orthogonality condition. So in the OLS setup, it turns out this is actually the identifying assumption. If we believe that neighbors are comparable, then this is necessarily true. But it is also the case that this can be true even if neighbors are not perfectly identical. We just need them to be identical in expectation. So it could be that your neighbors have all sorts of differences from you, except as long as those differences are sufficiently orthogonal to the differences in the X, you still get an unbiased estimate. It's not that your neighbors have to be totally identical to you. So if you have this condition so that your changes in the unobservables are uncorrelated with the changes in the treatment, then the SFD estimator is exactly unbiased. Of course, this may not happen, and so it's worth, I will show you in a sec what the omitted variables bias looks like and how we can think about why this is an improvement on the standard levels model. But just to, maybe because it helps solidify, what the estimator actually is, think about, a sequence of observations. So in space, so this is in a one-dimensional context, like the houses on the street I was talking about. You take your data, you difference the observations between each observation and its neighbor, and then you just run the regression. So in this context, it's quite easy. And what's nice is that you, like I said before, you can just use standard time series operators. So I actually wrote down the two stata commands. I don't know if everyone uses stata, but what you would do is you essentially tell stata that the number of the house number is time, right? And then you just take differences in house number and run the model, right? So it's very simple. You don't have to, you can kind of hijack your statistical packages, the time series procedures. So here's the question that Stephen had before. So suppose we have 2 dimensions. Well, now there's actually more degrees of freedom in terms of how we actually implement this. So here you can imagine each one of these squares is a pixel. And what you could do is you take your data and you set it up as if it were a panel, okay, instead of a time series. So here you might say the rows are like their panel observations, and let's set the columns to be like time. And so you actually have like a sequence of time series, okay? And then what you would do is you'd basically tell stata that instead of, you have a panel where latitude determines the panel unit and longitude determines time. And then you can, again, just hijack the time series operators and run a standard model. As an alternative, like I was alluding to, you could also do the same thing, but instead just arbitrarily decide to make the columns your panel units, right? And so now what you're doing is you're actually having 2 ways to estimate the same model using completely different types of variation in your data. And you can ask the question, which I'll show you later, is the beta the same using these 2 approaches? If they are the same, then you would have stronger evidence that the identifying assumption is plausibly satisfied. Okay, so I think what's nice, it's sort of the way I present it here, sometimes people are like, okay, but intuitively, why does this work? And so I think the way to think about this is actually to draw further on the analogy with time. It turns out in a lot of cross-sectional data sets, the variables that are causing omitted variable bias are slowly moving spatially coherent variables. So for example, thinking about like agriculture. If I was studying effects of temperature, but I didn't have rainfall data, as you traversed the South Island, like you would see that rainfall patterns don't move exactly with temperature, but they're sort of gradually evolving as you move from the East Coast to the West Coast. And there's sort of a spatially coherent trend across space in that variable. And so a lot of what SFD is doing is it's filtering out that low frequency unobserved variation so that it's just simply no longer in the data. What's also nice though, as I mentioned before, is that there's idiosyncratic differences between neighbors. Those are also eliminated because they're just going to be orthogonal to the treatment variable. That is sort of a second order benefit. I think filtering out the low frequencies in most contexts I've encountered is what is the main benefit. So the way to think about what that is doing, you could imagine, I give an example. So imagine you're on the East Coast and you are walking in a straight line across the country to the West Coast. So if you're doing that and you're taking measurements of average rainfall for each step, you can think of it almost as like it's a unit root process, where each observation, the rainfall levels you observe, are essentially the rainfall levels of my neighbor plus any difference between me and my neighbor. And so call x tilde sort of all of the sum of all changes up to the point where I am now today, starting, say, at the East Coast, some arbitrarily defined initial point. And so x tilde we call a spatial history, where it's kind of arbitrary where you begin, but it's as if I followed a path, what would I have observed? So here's a random sequence from a unit root data generating process, where basically you're traveling along and each observation is essentially the sum of its entire spatial history plus the innovation between itself and its neighbor. So this is actually a sequence of random draws. Here's actually another sequence of random draws. And what you see is they look very correlated, and this is the well-known problem that the time series with unit roots will be spuriously correlated. And so this is what happens a lot in many cross-sectional contexts. What spatial first differences do is it removes all of the information contained within the spatial history. And so you are only relying on the innovations that are occurring between subsequent neighbors. And so it has all the benefits of first differencing from time series in terms of filtering out those slow moving trends. To think about what that means formally, it's useful to decompose the form of the bias that we see. So what I've written at the top here, this is the estimated coefficient in the levels model, like we saw before, is equal to the true beta plus some bias due to the correlation between the x's we see and the c's that we don't observe. If we focus on this term here, which is the source of all the bias, okay, so we have x prime c alpha, we can actually decompose it by transforming each x and each c into the terminology I just showed you, where x is the sum of its spatial history plus an innovation, and c is the sum of its spatial history and its innovation. And so overall what we see is that the omitted variables bias is the sum of these four terms, or if we group them, these three terms. So we have these matrices, W1, W2, and W3. W1 is the correlation between each observation's spatial history in the treatment as well as the unobservables. And so this is the problematic term in most contexts, where you have large coherent patterns in some unobservable C that turn up and become correlated with the actual treatment variables you're interested in. W2 is the correlation between the spatial history of the unobservables and the innovations in the treatment, plus the history of the treatments times the innovations in C. And W3 is the correlation between changes in X and changes in C. So what happens is when we do implement spatial first differences, we eliminate W1 and W2 entirely. So those are zeroed out by construction. And so what we end up with is simply a bias that has the form of W3. And so before you might recognize this term, the identifying assumption was that this term is zero. Now, even if that is non-zero, you still get a huge benefit from implementing spatial first differences, because as we can write down exactly here, the difference between the levels estimator and the spatial first differences estimator is this strictly beneficial reduction in the bias, okay? And in practice, W1 is the largest term by far. Okay, so I see that I'm going a little slow, so I'm going to pick up the pace and just maybe skip a few things. The first thing I mentioned, the practical considerations to consider is the spatial density of observations. The units of comparison have to be similar to one another in order for this to make any sense. So here's a picture of Iowa in the United States, and we think it might be plausible to compare observations that are adjacent in this context. In other contexts, Russia and China are adjacent neighbors on a map like this, but we might not think that they're comparable. And part of the reason is because there's many elements within those units that are very far from the boundary. And so this seems like it would be an unreasonable context to try to implement something like this. There's a bit of formal treatment in the paper about this particular issue, which is what if you have some variable that causes both your treatment and unobservables? And it turns out that SFD is fairly robust to this particular context because you actually need the second derivatives of these two variables. So in this case, the second derivative of temperature with respect to elevation to mirror the second derivative of air density with elevation in this particular diagram I've drawn here. And that's actually fairly rare in practice. So just for example, if these were the relationships we were postulating, we were interested in temperature, we were fearful that some function, unobserved variable like air density was mattering, you could have these different setups. In the first two, you would be fine. You would estimate something that's unbiased. In the third one, you would have a problem. Okay, so we don't think it's not foolproof. You have to think carefully about what you're implementing, but it's quite robust to a variety of scenarios. And like I mentioned before, you can do a rotation of the coordinate system as an internal check. Oh, I forgot this. There's actually a last sort of robustness check, which is you can write down and difference to differenced equations. And so you can actually compute spatial double differences. And this is a completely different identifying assumption about there being orthogonality in the second derivatives. And if, it seems you can implement this to check whether or not you get the same coefficient. And if you do, it's not a guarantee that you have an unbiased estimate, but it seems like you're sort of putting additional restrictions on how the how the identifying assumption must be violated in order for the estimate to be off. Okay, so
Solomon,
yeah, go ahead.
Sorry,
yeah,
just for clarification, but in the much older literature on econometrics with spatial lags, you always have a weight matrix. And as far as I know, that literature has never really found a way to determine what the weight matrix should be. And you can choose different things like giving neighbors full weight and non-neighbors no weight. And I think that's what you're doing here. But of course, there's lots of alternatives too, of giving like second order and third order neighbors a certain weight as well. So to what extent can you take a situation like that into account here too?
So actually, it's a great question. And we have a whole section of the paper sort of trying to connect this to those existing literatures, because I think not everyone spends a lot of time with them. So in the context of having like a spatial weighting matrix, it's actually, those are sort of, they're both thinking about neighbors, but they're totally different use of space. So in the spatial weighting matrix, you're doing that because you think, for example, a neighbor's treatment might affect your outcome. Here, you're just using space for identification purposes. So what, in fact, what you can do is, I'm not answering the question of what the weights ought to be, but suppose you think there should be weights. You can actually write down the spatial weighting regression model that you would do, and then you can difference that. So you can actually estimate the causal effect of neighbor's treatment on my outcome by looking at difference between my neighbor's treatment and my neighbor's treatment. So you can use both methods just overlaid on one another, and it just behaves the same as any type of other OLS regression. So there's the existence of spatial spillovers, which is the context in which you use those weighting matrices, doesn't invalidate the model here. You could actually just estimate the whole structure of that model using this procedure. I'm going to skip the simulation and focus on two examples that I think help clarify what's going on, and then we can open up for questions. So the first example is to just sort of focus on a question that economists have studied for a very long time, so that if we get the right answer, we kind of know that we've gotten the right answer. So we ask, what are the returns to schooling? And can we estimate it by comparing neighbors along a road? So what we do is we just went to two different cities in the United States, and we looked for the longest road in New York City and the longest road in Chicago. And then we pulled all the census tracts along that road and are going to run a regression of wages on years of schooling, log wages on years of schooling, putting in no other control variables, okay? And so we sort of know that in a levels model, this should be biased. There's all sorts of things that will be correlated with years of schooling that should also affect wages. And we're gonna also estimate it in spatial first differences, where each census tract is differenced from its immediately adjacent neighbor. So it's essentially basically the example I showed you in the beginning. And in fact, we thought to do this test when we were writing out a description of what this model is. So what we're doing here, so what we do is we take 10th Avenue in Manhattan. So it goes from the north of Manhattan, the island, all the way to the south. And what you see on the right here is a plot of log wages and years of education as two different colors as you travel from 1st Street up to 207th Street. Okay, and it's very similar to what I was describing before. You have these very large, slow-moving trends where as you move through whole neighborhoods, you have gradual drift in both years of schooling and wages. I always tell people, I got my PhD at Columbia, where I actually lived right here on this block where Columbia is located, where years of schooling are very high and wages are very low. So what spatial first differences is doing is we're going to difference these time series, and we eliminate that slow varying trend from the data. And so this is the spatial first differences in these two variables, and we're just going to regress one on the other with no controls. We also do this in Chicago as a second test, just looking at I-90. And again, what you see are these large spatially coherent trends in both variables that lead to large omitted variables bias. But we eliminate those trends when we take the first differences in the data. So what you see here are a bunch of 17 different estimates of the returns to schooling in the United States from a previous literature review by David Card. And as people are familiar, it's always in the vicinity of 5 to 10%. What happens are when we take those two streets in those two cities and we estimate the same basic cross-sectional regression in levels, as you might expect, we get very biased estimates. Okay, they're very far from the center of the distribution. But when we take spatial first differences, we land right in the middle of the distribution. Okay, so it's the exact same observations, but just by removing that spatially coherent trend, we remove the influence of many, many omitted variables. Okay, so that's kind of a cute example. It's very simple. Now I want to show you something that's a little bit more complicated that might be closer to a more involved context for most research environments. So what we do here is we're trying to ask the question, what is the effect of long-term climate and soil on a single crop that's produced across the United States? Okay, so we're going to look at maize. And in my field, thinking about the effects of climate change, this is kind of like a famous question. How can we get at the effects of long-term climate? Because we can't necessarily change the long-term climate exogenously in a clean way. So people have always wanted to do the cross-sectional regression, but it's always been known that it's probably contaminated by omitted variables bias. And then people have always talked about soil quality mattering, but that was always considered so difficult, almost no one even tried it. So what we're going to do is we're going to take some data from a famous study by Wolfram Schlenker and Mike Roberts. And then we're going to take some other data from those same authors plus their advisors, where we look at soil characteristics and construct a balanced panel of observations. And we're going to collapse this whole panel down to a single cross section. So we're just looking at one snapshot of agricultural production in the eastern United States. In this region, we're going to run, like before, two models. We're going to estimate a levels model where we regress log of yields on temperature, rainfall, and soil quality. This has been done before with the argument, in some cases, for example, if you care about temperature, you need to control for rainfall and soil quality. We're going to do it again using the spatial first differences model. But one of the tests I'm going to show you is that we're going to say, imagine we care about temperature. Well, then let's pull everything else out of the model and ask whether or not the coefficient on temperature changes in spatial first differences, and ask whether it changes in levels, to sort of try to understand if we simulate a context in which these were unobserved variables, how much worse would we have done? So here are some results from levels. What you see here in model 1, we're modeling the effects of temperature. Essentially, you estimate a spline with a slope below 29C and a separate slope above 29C. We also estimate an effect of precipitation, which I'm just not showing you on this table because of space. And we also estimate the effect of 5 different soil characteristics. And so what you see are here, for example, there's been a lot of attention in the past on these coefficients. So what is the effect of hot days? And I think many of us would be very happy to get consistently negative estimates that were statistically significant here. What I'm going to tell you is that these kinds of estimates you shouldn't be satisfied with, right? Because -6 and -8 and -5 are all very different numbers. And so the fact that they differ across the columns in the table are an indicator that when you include information on soil quality, or between 3 and 4, you include information on soil quality and rainfall, you have a lot of omitted variables bias that's being absorbed by those additional variables. Additionally, for those of you who think a lot about agriculture, you might be surprised to see that here, soil erosion looks like it's quite beneficial for agricultural production. That seems counterintuitive and doesn't seem like that should be the answer we would expect. Here, it looks like it's highly statistically significant. So we wanted to implement spatial first differences, and this is where 2 dimensions starts to get more complicated. You look at this, it's not gridded data, and you ask, how do I assign neighbors? And so actually Hannah, my co-author, devised a very clever approach. And so what you do, what we did here, and this is not the only thing you can do, but it works quite well, is you define sort of something we call a channel. And you basically search, you move, in this case, east along your channel, always searching for the observation with the next centroid that is adjacent. And so here is a sequence of neighbors that we can treat like we're going to difference them from one another in the order that is drawn on the picture. And then we can set up another channel and do the same procedure again, making sure not to include the observations that have already been matched to a neighbor so that nobody's counted twice. And so then you just repeat the process over and over, moving south, okay? And what you've done is you've created something that looks like a panel, again, where the panel observations are the channels going vertically and time is going to the right. So we do this for the entire country. And so what you see here is you're traveling across states. And sorry, I'm going to show you just what the variables look like along a single one of these channels, okay? And so what you see are, in this case, the blue line is log of yields. The green line is our degree days, okay? So how many hot days you observe. And what you see are similar to what we talked about before, these slowly moving trends across space that are very spatially coherent and lead to omitted variables bias. On the right, you see the data when you take the difference along this channel. And so you remove those trends. And this is the variation that we use in the regression. So here are the results using spatial first differences. So it's the same as the table I showed you before, but it looks quite different. So here's what you see. So for example, the effect of hot days is now estimated in 3 different models to be somewhere between 4.73 and 5.12, okay? Even though in these models, we are including or removing a variety of controls. And so what I think that indicates is that when you stick in a new control variable, the variation from that variable was not present in the column 1. Okay, so including information on soil essentially doesn't impact your parameter estimate because whether it's observed or unobserved, the SFD estimator is pretty much unbiased in both cases. That type of across the board comparison you can actually make for any of these variables, right? You can look at the question of what is the best soil class, what is the effect? Well, across these 3 different models, we're getting the same estimate. And so we can treat each variable as omitted variables for the other variables in the model and make those types of comparisons. And now what we also see is that the soil erosion is no longer estimated to be beneficial for crops. Okay, soil erosion now appears to actually be harmful. Here are just some visualizations for those of you that think about maize yields all the time. Like these are the forms that we are very familiar with where crop yields increase gently as you increase temperature and then they fall off very steeply at high temperatures. And here are estimates for the effect of rainfall. One reason I show this is to show that we actually wrote down, as was mentioned before, sort of a complicated model that was a nonlinear model. And you can, as long as it's linear in terms, you can take the spatial first differences and still estimate a fully nonlinear regression model. Okay, so here's the thing that I'm most excited about. So what we did here is we said, look, we have this model. It's got a rich set of covariates. Let's go to each variable and pretend that there's covariates that we can't see. Okay, let's simulate different types of data environments in which this one was unobserved or another one was unobserved. And by doing that, we actually, given the number of parameters we have, we can construct 192 different regression models for each variable, pretending that the other variables in the sample were either omitted or included, okay? And then what we do is we re-estimate our parameters using the traditional levels cross-sectional estimate, as well as the spatial first difference estimate. And so what I'm showing you here are the distribution of coefficients that are estimated in those 2 different regimes using the full suite of 192 different regression models. And so if you focus here, so degree days above 29C, this is the effective hot days, for example. What you see in the levels model, which is the orange bars, is a huge amount of variability in your estimates. Depending on what control variables you put in the model or take out, you get different answers. The blue bars are indicating the spatial first difference estimates. And what we see is that it's pretty much immune to whether or not you can include control variables or not, because the omitted variables are not having a large influence regardless of whether they're in the model. And so what you see across all 8 different parameter estimates here is that the spatial first difference model is dramatically shrinking the amount of variance you get across model specifications to the point where it almost doesn't matter. You know, now here you saw before, soil erodibility was highly variable and positive. Once we do spatial first differences, it's very consistently negative at almost the same value across all the different models. Okay, so we take this as sort of our strongest evidence in an experimental context that this estimator performs well, regardless of whether or not you have observables or unobservables. The last thing I want to show you, which is just kind of fun, we talked before about the idea that you could rotate the coordinate system, and so you could go north, south, or east, west. Turns out you can, in this context where you have these irregularly shaped counties, you can do much more than that. So what we do is we actually keep the channels fixed and we rotate the map underneath it, okay, by 180 different degree increments. And we re-estimate the model 180 different times, each time basically using like a new data set that's slightly different than the others. And what you see here is just an example. The paper has more information. These are 180 different estimates of the effect of extremely hot temperatures, okay? And so what's exciting is that sort of we think we've eliminated omitted variables bias, because in order for the local conditional independence assumption to be violated, it would somehow have to be violated regardless of what direction you look in space, because we're getting the same, essentially the same estimate everywhere. Oh, and the last point is that we also try the spatial double differences robustness check, and it actually works quite well. So you can double difference in space, and it doesn't always work because you can introduce a lot of measurement error. In this particular context, it performed quite well. Okay, so we're over time. To wrap up, cross-sectional regression approaches have been plagued by omitted variables for a long time. We all know that. We think that spatial first differences here is a very simple, very generalizable solution for contexts in which observations are densely packed in space. And we hope that this allows researchers to go back to a large number of questions, like the effect of soil quality, that were largely considered off limits since the identification revolution started. What we showed you here were a couple of different geometries of how you can assign neighbors. It turns out you can think of lots of other creative alternatives. So for example, one graduate student at Stanford already has written code to take your sample and draw one long spiral circling inward. So you basically turn your 2-dimensional sample into a single 1-dimensional sample. You could also imagine going up levels in a skyscraper and comparing neighbors that way, or going along a river network and comparing neighbors. So there's just all sorts of ways you could set this problem up. We're very excited to see what people do with it. If you find a nice application, we'd be very happy to hear about it. And all the code that I've showed you today is posted online. So there's a whole R package that Hannah has written. And thank you very much. I think I'll take questions.
All right, well, thanks, Saul. I'll just get started by, well, actually, Trent, you're here, right? Yeah, so Trent, why don't you go ahead and ask your question from the chat, and after that, we'll take it from there.
Yeah, so first question was, Saul, was thanks for the seminar, it's really great. Could you apply this to variables other than space? I mean, I don't see why you couldn't take any continuous variable and apply this approach.
So yeah, so you're like jumping way ahead. So yes, it's actually, you could in principle, if you think you have another way to index observations such that adjacent observations should be comparable, whether it's a propensity score or something else, you could do it. So I think you could take the math and it would map very similarly to a variety of other types of variables. I think space happens to just be the context I guess I was thinking about. And we have a large number of problems that have those, where I think in the real world, there's just lots of things that are very spatially coherent, but I don't see any reason why you couldn't apply this even more generally.
Well, okay, yeah, no, yeah, the one I mentioned in chat is why couldn't you do it with income, for instance, right? Any continuous variable in principle, or combinations of continuous variables.
Yeah,
I guess you'd want to think about which were valid for your identification assumption. But then that's the raise of the question is what happens if, so two farms are in the same place, right? If you have the same value for this spatial variable.
So
wouldn't that be ideal for you? I mean, you're.
Yeah. That is in a sense ideal. So like the idea of having things densely packed in space is trying to sort of go into that limit. And so.
Right, and so then that makes me think, why wouldn't you use this tool to exploit discrete variables?
Sorry, like what do you mean?
Well, I mean, could you think of a binary variable as being your spatial variable? So.
Oh, yes. Right. So I think in that case, then we're essentially matching. We're in like a matching environment, matching on. That's sort of your.
I guess so. Yeah.
Yeah. And I think one way to think about this is it's a way to do sort of continuous matching in space.
Mm-hmm.
I mean, where you're essentially matching on like latitude and longitude. It's, right. I mean, in a sense, all regression is matching, but that's one way to think about this.
Okay, thanks.
Yeah, great points.
All right, who's next?
I think Bob had a question, I think.
Bob, all right.
Yeah. So really great seminar. I mean, I very impressed and very clearly presented. So thank you very much for that. It seems to me that, and I may not have the intuition here right, that the reason you want space is because basically you're assuming when you move along these spatially adjacent places that there's not a lot of action in these omitted variables, where there's maybe a fair amount of action in your treatment and outcome variables. And so you are able to eliminate a lot of the confusing noise from these unobserved variables while not really doing that much damage to your treatment and output variables. But suppose that if that's correct, I don't know if it's correct, suppose it were reversed. Suppose you had slow moving changes in your treatment and outcome variables, but a lot of action as you moved along your line in your unobserved variables. I mean, wouldn't that upset the kind of identifying assumptions you're using to make this work?
So that's a great question. So I think part of your question, and I apologize if this is not exactly what you're thinking, is kind of into, like I drew an analogy to regression discontinuity, in where you sort of, you hope, the way we usually think about it is we hope that all the omitted variables are moving smoothly in space, and then all, like as you say, all the action occurs on the treatment. The reason I pointed out that these are not exactly formally the same as doing regression discontinuity everywhere is that we don't actually require that to be true. So here's an example. So for example, this is a context that I was showing you before where we have the outcome and the treatment of interest, and they are both slowly moving in space. So what we're doing is we're saying, well, we're just not going to exploit that variation. So in a sense, we're filtering the data and we're removing all the slow variation, and we say we're going to just rely on these little bumps up and down. And that's all that remains after differencing. And so you're in a way, you're basically looking at the noise in your degree days as the identifying variation. And so it doesn't actually require that the treatment of interest is moving wildly. In fact, the thing that I skipped, so it's totally fair to have this type of question. We did a simulation to sort of ask this question, like how much variation do we need in our X to get the action that would identify beta? And so you can read the paper if you care about the math. I'll just focus on the pictures here. We basically make a variable X, we make a omitted variable C, and then those two things come together to construct some Y, which also has noise in it, okay? And so here we've made sinusoids because they have this nice property of looking like spatially coherent trends. And what happens is, even in this case, when there's no noise in your treatment, when you difference, you get very bad performance. So what I'm showing on this graph is a line of our estimated coefficient for both levels and first differences as we change the frequency of the sinusoid for the omitted variable. And the reason we do that is because we often don't know like what is happening with the omitted variable because it's unobserved. So we don't really know where we land. What you see on this graph is if the two things are completely in phase, you get a really biased estimate, no matter what you do, spatial first differences or levels, if there's no noise in your treatment variable, because you difference away all the variation that would be useful. But the second you introduce a very tiny amount of noise, so here what you see, the X's now have like this little bit of noise you can see on top. It still looks very similar to the omitted variable. But as soon as you do that, then the blue line here is showing you the average estimate for a large number of simulations of the spatial first differences estimator. And so what happens is the orange line is the levels. The traditional model would do very badly. You'd be way off. But at least the spatial first differences estimate is consistent, but there's an efficiency bias trade-off here. So there's a huge amount of noise here. But even with just a small amount of additional noise in X, so here's a context in which X now has a very large coherent signal, but a fair amount of noise on it, we suddenly have the spatial first differences estimator performing very, very well, regardless of what's happening with the frequency of the unobserved variable. And so it's not to say it works in every case, for sure, you're absolutely right, but there are some simulations that we can use them to sort of think through, you know, these kind of, like as you're posing these what if scenarios. And so we see that essentially you're exploiting the noise in X for identification purposes, and you need some, but not an exorbitant amount to get fairly good estimates, at least in the contexts that we've tried. Sorry, that was a very long answer. I'm sorry.
It was a very good answer, but Simona, you want to jump in and then Tom after that?
Yeah, I'm not sure. I mean, kind of related, I think. If you go back to, for example, this idea when you were having bandwidths within which you were moving from, you know, different countries along some kind of zigzagging, if you like. Just as well, I mean, that makes sense because, for example, you were thinking about temperatures and therefore going from, you know, west to east or east to west, whatever, makes sense because this would be reflecting probably also in patterns as well, I guess, or the other north to south, depending on. But in other contexts, perhaps this special dimension might be important to distinguish things that are somewhat similar or share similar characteristics, going from center to something further outside, like center and periphery instead, and having kind of rings instead, right? So I can imagine, you were saying that toward the end, like river, and if you think about agriculture, the access to water, irrigation system, then whether you have something closer to the river as opposed to not, that would make a difference, natural way of discriminating, you know, from in a different way, perhaps than just say, okay, now arbitrarily, I just get a grid and try to see which one is neighbor to whom based on that grid, right? So I suppose, depending on the question you ask, this can be adapted to different contexts. So rings, concentric rings could be one way. If you think about urban center and then further periphery or something, or, you know, depending on the shape of the territory, could be ellipse or kind of concentric ellipse, I don't know, something. Is that something that's what, in a way, this could do?
Yeah, absolutely.
Right?
You're totally right. Yeah. I think like the articulation of the approach is sort of very general. You find neighbors that you think are comparable, and you try to set them up in a line somehow so that everyone has a neighbor. Yeah. And then, yeah, but how you do it, you know, is like, I think up to you for sure.
And then it brings me to the kind of next point that for now, although this moves the way in which you classify things belonging to which kind of coordinate or category, if you like, is according to one dimension, you know, some spatial dimension of some kind. But what if you have a multidimensionality or ways in which you can classify things? Can this be augmented by that? You see what I mean? You could be in terms of latitude and or is this actually urban or not, or some other characteristics on top of that you could augment the way in which you define similarities, if you like.
Yes. So I don't know if I have the picture here. Oh, I don't have the picture here. So for example, in this context, what I'm showing you here is the state of Illinois, which is good for an example illustration because every county grows maize. But in reality, when we implement this for the country, there's gaps because there's many counties that you drop out. So I think, what you do is you basically, it looks like an unbalanced panel across space because there's holes. And it sounds like what you're saying is you would stratify based on some other variable, mask out the locations that don't sound
so overlaying different filters.
Exactly, and then run the procedure. So I think I think that would make total sense.
Yeah, thanks. Yeah.
Okay, Tom, you want to go ahead?
I think mine is somewhat related. Kind of in your picture of the houses, there was one house next to the other, and the distance was always the same. And so I wonder what happens if there are some missing houses, and so the distance between houses varies. And then, kind of in some way, the closer houses are better matches, and the farther away houses are worse matches. And I don't know, shouldn't you take that into account in some way? Or
that's a great point, and I think I would love if someone would think about that. We haven't dug into that, but I think. And like we were just saying, like when we did it with counties, we came up with a certain tolerance, right? And we said, like, for counties, we just want them to be adjacent. But as you're pointing out, like some types of observations are point data, and then you have to have something that's a bit more manual in terms of saying, like, if the distance becomes too great, we don't tolerate it, or maybe we downweight it or something. That's a great question. I haven't really thought about that, but I'm sure you could get a more efficient estimator if you applied the right weighting scheme. Yeah.
All right, 4:01 p.m. New Zealand time, much later p.m. California time. So let's thank Saul for his presentation and his time he spent with us. So again, thank you very much, Saul. That was a great talk, and again, we much appreciate your time taken to talk to us today. Thank you.
Thanks for having me. It was a pleasure.
Thank you so much. And by the way, if I may, there was a request sent to me privately, but I just take the opportunity to mention with everyone, if those that are speaking would like to share the slides, either ahead of their talk or after the talk, I'll be very happy to post them on the website as well. So that's also for you, Solomon, in case that's okay with you. Feel free to just let either Dennis know or myself, and I'll make those available in addition to the recording. Thank you. Bye.
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 Okay, everyone emptying out. All right.